All right. So today we're going to finish with the topic of vertical stress and pore pressure. Before we do that, let me do some house cleaning. I want to let you know that we have, you have a homework due by Friday related to the topics that we have been seeing. I'm not quite sure if we're going to see in detail what you have to do today, but if not, we'll finish that on Wednesday. So don't worry, you should be able to do it. It's not too difficult. And another thing, I have some good news for you. Thank you very much. There's something related to this. I'll tell you later. I have some good news. I don't know if you know student Athena Ko. She's going to be the geomechanics tutor for this class, and she did an excellent job last semester in this class. And she's going to help you out with homework and with anything that you may need for this class. Okay? If you don't know her, I'll send you later on her email address, and you can contact her if you need help. All right. So let's continue with our class. And for that, let me go to the document. If you remember, on Friday we were talking about Galveston, and we were talking about Galveston, that the water is very muddy, and the reason for that is that it's charged with sediments. We have muddy waters in Texas and Louisiana, but also we have a Gulf of Mexico, right? And we have oil there. You may go to Florida, but you will not have muddy waters, but also you don't have as much oil as we do. So there is a trade-off in there. But anyways, we were saying that when the rate of sedimentation is much higher than the rate of pore pressure diffusion, which means how fast water can escape out of the pores, then when the sediments drop too fast, the water cannot escape, and that creates a locked pore pressure. That it's a function of time, but some of these sediments, they have such a low permeability that it can take thousands to hundreds of thousands of years for that pore pressure to become hydrostatic. Probably in 1 million years, it will go to hydrostatic. But at this time, in several sedimentary basins, pore pressure has been locked in and it's releasing very slowly as a function of time. But if you go to drill today, you will see that there is a pore pressure that might be higher than hydrostatic. So our objective now is to take advantage of this trend and calculate pore pressure based on properties that we can measure from well logs, and also with parameters that we get from the laboratory. Let me repeat one more time that total vertical stress is going to be your best friend, and it's the first thing that you have to calculate. Pore pressure, many times you do not know it. You may estimate the value, you may assume what the value is, for example, if it is hydrostatic, but many times you do not know this, and actually there is a lot of research and development going on targeted to calculate more accurately pore pressure, because it's a very important variable, and many times it is not hydrostatic. Today we will see one method to calculate pore pressure when you have this type of overpressure, and it is very popular in the Gulf of Mexico. All right, so let's do that. In order to do that, first we'll do the case without overpressure, and then we'll do the case with overpressure. Okay, so we're going to go offshore. This is water.
paper down a little bit?
Yes. Many times, guys, I do not see what I'm seeing over there, what is showing over there, so let me know if it's too small, it's too big, if the autofocus is not working well, because I'm also looking at the page. Okay, so if you go offshore and you have sediments which are, let's say, mostly sand with silt, and let's say also some clay, but not too much, as you go deeper, and we're going to assume now that there is a hydrostatic pore pressure, in this case, as you go deeper, the pore pressure is going to go up, the total vertical stress will go up too, and remember it's going to kick off here from the seafloor. And let me ask you, what would you expect about porosity? Of course, where there is no rock, there is no porosity. But when we are in this region, should porosity stay the same, increase, decrease? What do you think? As we go deeper, the effective stress gets higher and higher in this particular case, and porosity should decrease. So let's say that we start at some point over here, and as we go deeper, porosity is going to decrease. Why? Because you have more effective stresses. Effective stresses are the ones that add forces on grains and make, for example, pores collapse, and therefore the higher the effective stress, the more compact the rock is going to be. This trend in which effective stress always increases, we could call it something which is normally compact, or a process of normal compaction. And under this condition, we can write an equation for porosity. This is just one of a few equations that tell us that the porosity is going to depend exponentially on effective vertical stress. And so the bigger the effective stress, the smaller the porosity. When effective vertical stress, in this case, approaches 0, then this will be 1, and the porosity will be just the, in this case, that porosity. And whenever this one increases, porosity will increase. It's just an equation that helps us tell what is going to be the variation of porosity with effective stress. And these two are parameters of such equation. Sometimes you can measure those parameters. For example, if you know there is a place with hydrostatic pore pressure, and you measure porosity, for example, with neutron porosity in a wellbore, if you know effective stress, if you know porosity, you can get this equation. Some other times, you can get samples from cores, and then take them to the laboratory, and in the laboratory, increase effective stress so that you can also measure porosity as a function of stress. Those two methods are available in order to characterize a given sediment. Of course, different types of sediments are going to have different parameters. For example, the more clay you have, the more compressible the rock is going to be. Okay, so higher effective stress, lower porosity. That's the concept. But that's what happens when there is something which is normally compacted. As we were discussing last class, sometimes we go into these sedimentary basins in which you can find layers that are made of quite a bit of clay, and probably some silt too. There's hardly only clay alone. And let's say that here we don't have any clay, we just have sand and silt, so it's relatively permeable. And here we have again clay, let's say sand, and in this case a little bit of silt. If the rate of sedimentation is higher than the rate of pore pressure diffusion, we're going to have an anomaly. So as before, let me draw the pore pressure in the water section and in the permeable section as just a line. Same as before, vertical stress is going to kick off from there. And let's say it goes over here. When we have now a low permeability layer, and if again the rate of sedimentation is higher than the rate of pore pressure diffusion, we're going to start to have an anomaly here in the pore pressure, and this pore pressure is going to depart from this trend, and it's going to get higher. And this is what we call overpressure. Okay, so we knew this from before, but let's see what is the new thing. The new thing is related to porosity. So it's going to be porosity. This is C. Let me extend these lines. If effective stress increases with depth, porosity should decrease. Let's say it decreases up to that point. But what's going to happen now if the effective stress starts to decrease with depth? What do you think is going to happen with porosity? Do you think it's going to stay the same, or will it increase?
Increase.
Will it continue decreasing normally as expected? Well, for sure it's not going to continue as this, because the pore pressure is not the same. So it may decrease more slowly if the effective stress still keeps on increasing, but not as much as with higher standard pore pressure. Or as we see over here, it apparently the effective stress is about the same for some time, and they may even increase. So this anomaly of porosity that we're going to measure it with logs is the one that's going to allow us to predict what the pore pressure is when we don't know the pore pressure. And in places in which the formation is very permeable, like say over here, even you can make a wellbore here. If you isolate this section and that section, and you put the pore pressure transducer in here, this formation is so permeable that the water is going to fill in the wellbore very quickly, and it's going to equilibrate with the pressure in the wellbore. So you can measure the pressure with a gauge. But when you are in formations that are too tight, the matrix of the rock may be so little permeable that even if you put a gauge inside the wellbore, the water is not going to fill in so quickly the wellbore such that this fluid is in equilibrium with the fluid in here. That's, for example, a problem too for measuring permeability in shales, because even if you put a wellbore there, which is empty or with a gas, the fluids are going to come very slowly to the wellbore, and the pressure is going to go up with time, but very, very slowly. So it's not economical or practical to measure pore pressure by putting a gauge over here. You need to use an alternative method. And in this case, we're going to use a method that uses the actual porosity measured from well logs in order to predict what is the pore pressure. So to put a little bit more of reality here, what methods we use to measure porosity in wellbores? Any suggestions? Okay, guys, you just reminded me. I need to print out the roster of the class, and I'm going to give you extra point for class participation. Something we didn't say, because I didn't have time also for the syllabus. But I'm very strict with the cutoffs. All right? So for example, the cutoff from A to A minus is 93%. If you have 99.999999, to me, that's lower than 93, okay? So the cutoff is 93. However, if you participate in class, if you are active, if you're involved, I'm going to give you extra points that will help you convert a 92.999 on a 93, all right? I don't have my list right now, but I'm good remembering faces and names, so please help me